Hi, in this video I'm going to discuss about the Ensemble learning machine learning algorithm. I'll be discussing particularly about the bagging algorithm. So what is bagging? We have learned in our previous video about decision tree, right? So decision tree is a supervised learning algorithm which is used to classify your data. You can also use it for regression problems, but it is very popularly used for classification problems. Now, bagging is another algorithm which is an improvisation to decision tree. You can combine many decision tree to classify your data, which will be performing better than a single decision tree. And the method of doing that is known as bagging. Okay, so let's get started. Now we all know that there is no algorithm which can predict everything accurately. That's impossible. Most algorithms will fail to predict all data points correctly. So the idea is to maximize the correct prediction. Okay. So the important thing to know is to have high accuracy, or to just maximize correct predictions. So that's the idea. And for the learning algorithms, you have many things to consider. Okay, so different learning algorithms uses different algorithms, different parameters, representation, training set, and subproblems. So depending on these factors, you choose the best learning algorithm for a given data. So we have learned in decision tree, we recursively classify your data into various subgroups and take the majority count, majority voting, and choose for the selection. Right? If you're not familiar with the decision tree algorithm, you can check the video on decision tree on my channel. The link to the video is given in the description section of this video. So in decision tree, you just classify data, and in the terminal node, this is the terminal node, you will have different points. Let's say these are dot and there are circles, and take the majority count. Okay, so the majority over here is dots. So we say that this particular class belongs to dots. Okay, had it been more circles, we could have said that it is circles. So that's the idea. Voting, selecting the class outcome of the classification through voting. But it's just a single classifier. When you have multiple decision tree in place, you will have multiple decisions for a single data point. Okay, so for a single data point, we can just take an example. So here is an example. Okay, so this is our training set. We have got default. We have we'll take lone data. Okay, default data and non-default data. Default, null, default. Then third one is non-default again, non-default, default, and default. So that we have got 6 observations with 3 default and 3 non-default. Okay. So the classifier 1 predicted this data point to be non-default. Classifier 2 predicted it to be non-default. Classifier 3 predicted it to be default. Now you have 3 classifiers. 2 of them predicted it to be non-default and 1 of them predicted to be default. The majority is non-default. Hence, we will conclude that this would be a non-default classifier, non-default data, which is a wrong prediction, of course, because this is default. The same will happen for all the data points. So what essentially we are trying to do here is that we are combining the outcome from different classifier, and then we are combining the result to come up with the final outcome. Now we have a different ways to do it. It's not that simple the way I explained to you. There is mathematical way to do it. Okay, so a single classifier would do something like this. You have outcome y, which is a linear combination of weight with the classifiers in place, and D represents each one of your decision tree, and you could have several decision trees in place. Okay, and the weight should always be greater than 0, which is expected, and the sum of the weight is always 1, because the probability or the proportion should always sum up to 1, right? And that's the way you will classify your data. Depending on what you get here will tell you or tell us what exactly should be the outcome of this classifier. This will take into consideration the outcomes from multiple decision trees. So that's the idea here. Now, bagging is otherwise known as bootstrap aggregating. Now, bootstrapping is nothing but when you have a sample and you repeatedly take subsamples in place, we call that as bootstrapping, and that is used in many modeling exercises where you do that for validating your model. Sometimes even building your model you use that. Bootstrap is otherwise similar to what is known as a resampling, although there are differences, but there is similarity. Resampling means getting different samples from the same sample again and again with replacement. Okay, taking multiple samples with replacement, that means the same observation can be in different subsamples. Okay, so take m bootstrap sample with replacement, that's the point to be noted. Train m different classifiers, so we have m different samples, so you will have m different classifiers, which could be decision tree, linear regression, and so on. But for bagging we would use a decision tree instead of a linear regression on those bootstrap samples. For a new query, let all classifiers predict and take an average. Okay, so once you have m classifier, you will have m number of outcomes, right? M outcomes. For every observation in your training data, you will have m outcomes, and out of these m outcomes, just take the majority count. Okay, if m is 5, and you have a classification of 0, 1, and there are 3 0 and there's 2 1, the outcome is, the majority is 0, so the outcome is 0. That means the final answer is 0, and you will do that for every observation. So that's the idea behind bootstrap aggregating or bag. If the classifier makes independent error, then their ensemble can improve performance. So what is important here is to know that there are two steps, right? In one step you build model for each one of these smaller samples, and the second step you aggregate them. While aggregating, you do not just simply count the way I counted. You actually do it through providing different weights. If something has been misclassified, you provide them higher weights. And how is that done? We'll just see. So that's what we saw in both bagging. Boosting is somewhat different from bagging. You train classifier in a sequence. A new classifier should focus on those cases which were incorrectly classified in the last round. So this is a major difference. A new classifier should focus only on those cases which were incorrectly classified in the last round. And then you combine classifiers by letting them vote on the final prediction. So the final second step is somewhat similar, but the first step is different from what is there in bagging. Each classifier is weak, but ensemble is strong. That means each classifier, the smaller classifier, they may not be very strong, but when you combine all classifier, when you combine them, right, you get a stronger classifier. So we'll take an example of what is known as AdaBoost algorithm. So adaptive boosting is what is in short known as AdaBoost, and we'll see what how an AdaBoost algorithm can be used to classify your data and improve on the performance. So all we are trying to do is just minimize the error rate. Okay, in a single classifier you probably have higher error rate, but in an ensemble one which combines multiple classifier, you will have lower error rate. So in this example you can see a single classifier doing the bad job. If you take this one, this classifier, it is doing a bad job because many of these negatives are also there here, and it's not able to classify. Same with other two classifiers, right? But when you combine them with some sort of a weight, it is a perfect classification, a near perfect classification that you can see here. Okay, Um, that is the idea behind combining classifiers to get higher prediction, because there is so much of non-linearity in your data, non-linearity, that a single classifier, a linear classifier, is unable to classify your data. You should have multiple classifier, combine the advantages of multiple classifier, and then use for higher, better prediction. So the idea is to adaptively weight each data case. So the data cases which are wrongly classified get higher weight. So that's the idea here. So a particular observation, if it gets wrongly classified, then it gets higher weight in the so there is a sequence, right? That's the difference. In boosting, you have sequence of classification. It doesn't happen all of a sudden, like in bagging. In bagging, you will have everything at the same time, but in boosting there is a sequence. So if it gets wrong in the first tree, it gets a higher higher weight in the second decision tree or second classifier, and then it gets combined. The entire classification gets fine-tuned with each step, and the final step would of course combine the result, and that would be a better result. Okay, so the idea of second classification is same, except the first one is different from what is there in back. And the way it is calculated is that, and in any modeling exercise, you cannot trust the error rate in training dataset. So you always do a cross validation on the test dataset, and that's what when it's done, you come up with a final classifier by cross validating with your test data and ensuring that your model is performing well in the test data as well. So here is an example of taking a boosting using a picture. So with this training dataset, so each observation has been given equal weight in the training dataset, and we got something wrong here. So this is the first decision tree model which got two of them right. So this observation got right, this observation got predicted to be right, but there were two wrong predictions. Now the point here is that in the next decision tree we will give higher weight to the wrong prediction. When we gave higher weight to the wrong prediction and relatively lower weight to the correct prediction, we got three right. First one right, second one right, third one right. But the last one, which was right in the which was correct in the previous decision tree, is now wrong. And the next step will do exactly different. Here we have right, so we'll just lower its weight, and so wherever it is right, we'll just lower the weight. You can see the size of this, it is going down. Here also it's a bigger size, but it has gone down here. So if it is right, it is going to get lower weight. If it is wrong, it will get higher weight. So this is a smaller one, and look, this is much bigger. Now we have a much better prediction. Okay, now we have right and wrong, but there are still two misclassification. Now again we'll do the same logic, we'll apply the same logic. Wherever we have got wrong, we'll just increase the weight, and then we increase the weight. Here we got wrong, so we increase the weight. So in just 4 trees we got everything correctly. Of course this will be cross validated, because getting everything correctly is not a very good sign of a model, because not everything can be classified correctly. So if that happens, then there is a clear case of overfitting of the model. But one thing is very clear, that with sequential building model of decision tree, you can combine the result and keep on changing the weight for each of these observations based on whether you have got a correct input, correct prediction or wrong prediction. By increasing the weight of the wrong predicted value, you can get to much better accurate result with few sequences. And it can also be understood in a different way, where you have bunch of data points to be classified, and in the round one you come up with some sort of a classifier, and that does a bad job. It just to classify pluses and minuses, and it does a bad job. It's not able to classify. In the second round, it is able to do it for negatives, but it's again doing a bad job. In the third times, we also use another classifier, which again using a bad job. So if we're getting something wrong, we are giving more weight. If we're getting right, then we're giving less weight. If going by that idea and when by combining with some sort of a weight, and of course the weight would depend whether you have correct prediction or wrong predictions. And then when you combine all three, you will get to the final results. And that's the idea of AdaBoosting or adaptive boosting. Now, the idea is so the weight that you decide, the weight is very much dependent on what the input is, what the input data set in the training data set. So that can also be automated with some sort of an algorithm or some sort of changes in the way your data is being provided maybe. Okay, when you have independent trees and you combine them in some sort of way, use some sort of function, right? And function has several weights, right? These are weights, which these are weights provided to each individual trees, and that is also some sort of a learning, and it's popularly known as stacking. So that's about using multiple decision tree to get a better result. We'll see in one of the example, we'll take R and solve one of the classification problem using boosting and bagging algorithm. Thank you.